This video will explore the illusion of apparent K-RISC, unfolding the microscopic truth of thermally activated delayed fluorescence. We will show that the apparent rate is not equal to the microscopic rate. The microscopic rate is the true molecule-level T1 to S1 transition rate, independent of radiative branching. The apparent rate is an effective rate extracted from macroscopic delayed fluorescence lifetimes and is diluted by state coupling and excitation cycling. Molecular cycling, from S1 to T1 and back, is the mechanism of dilution. This cycling process makes the net removal of triplets slower than the microscopic upconversion rate. The coupled master equation provides the standard kinetic backbone for TADF. It explicitly defines the microscopic K-RISC as an internal step within this coupled system. We justify the quasi-steady-state assumption by observing the singlet and triplet population decays. During the delayed regime, singlets relax instantly relative to triplets, enabling a separation of timescales. Filtering the exact solution using an asymptotic expansion filter leads to the slow delayed decay rate. This rate, K-D, is defined as the triplet loss rate plus the microscopic K-RISC multiplied by a factor related to cycling probability. The term 1p represents the probability that once the system reaches S1 via RISC, it does not immediately hop back to T1 by ISC. This is the net triplet removal per RISC attempt. Comparing the naive lifetime extraction with the master equation shows the critical difference. A small prompt fluorescence quantum yield can make the lifetime-based apparent K-RISC dramatically smaller than the microscopic K-RISC. We use two mathematical lenses, the master equation, which deals with continuous time and rates, and the Markov chain view, which uses discrete time, probabilities, and yields amplification identities. The geometric amplification cascade illustrates the probability of a photon being emitted given the system is in T1. The term 1/1 minus R-P is the mathematical representation of the multiple S1 to T1 loop amplification factor. By synthesizing the Markov logic and the master equation, we find a unifying truth. Both lenses prove that the net removal of triplets is dictated by the microscopic rate, which is strictly diluted by the cycling probability. We begin the diagnostic dashboard with quenching calibration using the Stern-Volmer model. The two-site nonlinear model predicts a PL reduction factor that matches the experimental results. Next is yield separation. Assuming oxygen kills the triplet-mediated part, we can separate the total oxygen-free PLQY into prompt and delayed yields, resulting in strictly defined separations. Step 3 involves rate calculation. We calculate KPF, KISC, KDF, and the K-RISC apparent rate using the prompt and delayed lifetimes and yields. The true microscopic transition reality shows the flawed macroscopic observation versus the true molecular reality. What standard experimental shortcuts measure as a slow rate is a fundamentally fast microscopic transition, heavily diluted by rapid back-and-forth molecular cycling.